Good afternoon. Thank you for the kind invitation to speak this afternoon. It is a great pleasure to return to Japan to take part in the Shonan Special Seminar on Cyber-Physical Systems and to take time out from the seminar to meet with you today. I have been asked to speak about our experience in transferring advanced technology from academic research into industrial practice. This is experience gained in the Center for Software Reliability, which is part of the School of Computing Science in Newcastle University in the northeast of England. From now on, I will refer to the Center simply as the CSR, because that is what all its friends call it. Our work in the CSR aims to improve the quality of life and the productivity of industry by equipping engineers and researchers with the mental and technical tools to deliver systems that justify the dependence that is placed on them. Making progress towards this goal entails ongoing dialogue between academics, industry, and wider society. The central part of this seminar concerns lessons learned about the academic-industry dialogue through a reflection on a series of key projects that we have performed in the CSR in recent years. But first, after a short introduction, I will place the CSR in its local and national context by describing Newcastle and its university. Later, I will concentrate on our experience transferring advanced engineering into industry, both the positive successes and some of the difficulties that we have encountered. Our research and industry collaboration concerns the design and delivery of systems that are dependable. However, the complexity of systems is rising, partly because businesses and citizens want to gain the maximum value from increasingly mobile but networked devices and systems. The methods that we have traditionally used to ensure high dependability have required relatively stable system architectures with centralized control. We have developed system models during the early stages of design and have focused on verifying to a high degree of confidence that software implements correctly the behaviors permitted by those models. Modern systems do not have all these properties, so it is difficult to know how to deliver dependability in such situations. However, it is clear that assurance and evidence are still needed as a basis for dependability, but that methods must be multidisciplinary in order to cover the range of behaviors and interactions between software and the environment. Here, then, is the question underpinning the work I will describe in this seminar. Can we develop multidisciplinary, rigorous, and yet practical methods and tools for modern, dependable systems? I emphasize the need for practicality in industry. We must think carefully not only about what theories, methods, and tools are being developed, but we must also think deeply about how we ensure they are the right technology to solve the real problems faced in industry and that they are delivered to potential users in the right way. My slightly controversial view is that successful take-up of advanced technology for dependable systems therefore requires dialogue between the developers of methods and tools and their potential users. I am uncomfortable with the words technology transfer, as they imply movement in one direction. It might be better to think about co-development of technology for dependable systems design, in which we give greater emphasis to listening to one another, from the practitioners on what is important, and from the researchers on what is possible. In the remainder of this talk, I will introduce our research in the CSR at Newcastle and tell some stories about how our approach to technology development for dependability has evolved over the years. I will finish by discussing how we propose to meet the new demands for flexible, networked, but dependable systems in the future. First, let me place our group in its geographical and historical context. Then I will go on to describe some influential projects. This image shows the city of Newcastle upon Tyne in 1832. Known simply as Newcastle, or as it is pronounced by its locals, Newcastle, the city is on the north side of the River Tyne, which flows from west to east across the north of England. Over the centuries, the city was nearly destroyed in conflicts, many of them with Danish invaders. But as you can see, we are good friends today. The defensive castle was constructed in 1080. Parts of it remain in the city today, and you can see it in this image, overlooking the River Tyne. It is perhaps typically English that nearly 1,000 years later, we still call the city Newcastle. The city is close to the sea, and it sits on major coal reserves, so that by the middle of the 19th century, not long after this image was published, it had become a thriving center of the Industrial Revolution. This slide shows some images that hint at the strength and depth of the engineering traditions in Newcastle. Driven in part by the need for powerful engines to assist with the mining for coal in the region, the city became a center of innovation and manufacturing in steam engines and powered seagoing vessels. George Stephenson built some of the original cutting-edge steam locomotives here, while the shipyards of Armstrong and others on the River Tyne equipped the world's navies, including that of Japan, through much of the century. The house shown here on the upper left is Armstrong's country home, Cragside, the first house to be lit by hydroelectricity. The city was once at the heart of what must have seemed like the Silicon Valley of its day. It had the first public road to be lit by incandescent electric light bulbs. The city saw the innovation of the first steam turbines and safety lamps for mining and many other inventions. Armstrong was one of the major benefactors who helped in the establishment of higher education in the rapidly urbanized Newcastle. The need, not only for professionals in medicine, law, and other disciplines, but particularly in science and engineering, led to the establishment of a series of colleges that eventually became Newcastle University. For the university today, the goal is to be a world-class civic university. This means a university that continues, like its original colleges, to undertake research and deliver teaching of the highest standard, but focused on areas that are civil and social priorities. We have three main themes: sustainability, aging, and social renewal. Our priority in the Faculty of Science, Agriculture and Engineering is delivering sustainability, technology that makes our industries successful and our communities and systems resilient. Here is a picture of part of our university campus today. It is a strange mixture of buildings from the 19th, 20th, and 21st centuries. Within the university, computing has been a major area of research and teaching for over 50 years. Let me say a few words about computing at Newcastle. The upper image shows Dr. Ewan Page, the founding director of the computing laboratory at Newcastle, at the console of a Ferranti Pegasus computer in about 1957. The laboratory began offering a numerical analysis course as part of a degree in mathematics and went on to offer the first undergraduate programming courses in the UK. The lower image shows a student working hard in our laboratories today. The School of Computing Science is now a moderately sized one among the UK's Russell Group of research-intensive universities, with degrees offering specializations in each of our research areas. Although he appears to be playing at a games console, the student is in fact working hard. He is in the Games Engineering Laboratory. Our degrees in games and virtual environments are unique and are focused on the hard, high-fidelity, hard computer science underneath games, such as the design of highly efficient, high-fidelity physics engines, and on novel applications in areas like assisting the recovery of those affected by illness, such as stroke. The graduates often join small computer games developers springing up in the region around Newcastle. These two pictures reflect the fact that just as Ewan Page was providing a computing facility to advance science and engineering, today we undertake research that is guided by a real-world purpose. And now, the Centre for Software Reliability, CSR. CSR, the Centre for Software Reliability, is a grouping of members within the School of Computing Science. It has a sister centre at City University in London. The CSR's focus is not only on software. In fact, the full name of the CSR is the Centre for Software Reliability and System Dependability. CSR works both on the development of foundations and on methods and tools. We have been involved in some very unusual and long-running research and innovation projects. 3 are mentioned on this slide. We will discuss the third one, deploy, in greater detail later in the talk. However, I should mention the others. The Dependable Computing Systems Centre was entirely sponsored by industry, by BAE Systems, and it lasted for 16 years. Over that time, we developed process improvement teams within BAE Systems to appraise the state of the art in several areas and to develop new safety analysis, human-computer interface, requirements analysis, and design technologies. Next, the DIRC project was a very unusual interdisciplinary collaboration between computer scientists, psychologists, sociologists, and others in the achievement and understanding of dependability. On the next few slides, I would like to mention 3 principles that I believe are very important for our work in the CSR. First, systems, not just software. It is important not to view software in isolation. Delivering dependable products means understanding the functions delivered by the system as a whole. Traditionally engineered products, like the beautiful 1939 Bang & Olufsen Beolit 39 radio shown at the top, were developed from components acquired for the purpose. Now, however, we generate systems of systems from multiple networked devices streaming data from multiple sources. The bottom picture on the diagram shows what Bang & Olufsen produce today, networks of devices. Understanding the dependability of these new, highly dynamic structures is a driving challenge for our research, as it is for business practice. A few words about the word dependability. On this slide, I have a classical definition of dependability from the computing literature. Dependability is the ability to deliver a service that can justifiably be trusted. The key word here is justifiably. It is important to be able to produce evidence on which to base our judgments about whether to trust a system with our data, our property, or our lives. The word dependability covers a range of attributes, including safety, reliability, and security. Whichever property one is talking about, there are threats to dependability and means to provide it to some level of confidence. My second principle for work in the CSR is confidence, not simplistic certainty. This principle is that certainty is a rather oversimple idea when we think about system dependability. In our work, we understand the value of mathematical model-based techniques in delivering a level of confidence about the properties of systems, such as their safety or security characteristics. However, proving properties about such models is not the same thing as guaranteeing them. We look to model-based techniques that promote abstraction and rigorous analysis as a way of increasing confidence. However, these must be seen as part of the larger picture of gathering evidence that is strong enough to allow us to place reliance on the system being engineered. On this slide, I have shown a picture of a railway accident at the top, and at the bottom, a picture of the architecture of a system of systems, which is the system of systems used in northern Italy to manage response to accidents such as this. We take these kinds of description of the system architecture and generate formal mathematical models that allow us to increase confidence in the properties of this system of systems. My third principle for our work in the CSR is that the development of theory is guided and focused by the needs of practice. In the CSR, we place a lot of emphasis on professional development. This is either done by teaching in the conventional university sense or by delivering professional support. We run the United Kingdom's industry club for practitioners in safety-critical systems. This has prospered for over 2 decades and has provided us with many valuable insights from industry. We are careful to run events by and for practitioners and do not treat the club purely as a showcase for abstract academic research. In return, we gain a great deal of the focus that we require for our own research and a strong sense of what is and what is not relevant to industry need. Following the principles I outlined in the preceding slides leads CSR to have a more varied portfolio of projects than might be expected of a pure research group. Here I show some of our current projects. Some of these cover security issues, while others are about safety, for example, in increasing the capacity of railways. Some are quite general, such as our projects on ambient systems and taming concurrency, while others are relatively close to industry application, such as work on e-voting. Funding comes from sources that reflect these types of project. In the United Kingdom, the Engineering and Physical Sciences Research Council, EPSRC, funds the majority of academic research from foundations to relatively low technology readiness levels, while the Technology Strategy Board, TSB, funds projects that take ideas forward to industry application and realization in products. Newcastle University is one of Europe's leading institutions at gaining research funding from the European Union. In Europe, the European Research Council, the ERC, supports international research collaboration on a systematic basis through competitive funding calls. The European Commission, the EC, has led a series of 8 research and innovation framework programs that have funded a great deal of our work and allow strong international collaborations to develop, such as the link between Newcastle and Aarhus that you see here today. Their projects are typically focused more on increasing industry readiness levels of technology. I hope that I have provided a sense of the context of our work, geographical, historical, and technological. In the next part of the talk, I would like to review some projects in which I have been privileged to participate while a member of CSR, and which I believe teach us some lessons about the dialogue between research and practice around advanced dependability methods. I will look briefly at 2 older projects, and then in greater depth at 2 more recent ones. All of them had strong industry involvement in cooperation with academia. First, the BAE Systems Conform project. And this was my first project with Professor Larson. This was an application experiment funded by the European Commission under the European Systems and Software Initiative, which we sometimes call ESSI. It took place as a result of our good links with BAE Systems, or British Aerospace, as they were then called, during the years of the Dependable Computing Systems Centre that I mentioned earlier. The project was the parallel development of a trusted gateway using conventional and formal methods. A trusted gateway is a small security-critical system component that separates and routes messages according to the confidentiality of their contents. The project allowed us to demonstrate cost and quality improvements associated with the use of structured and formal methods. Note that this is certainly not a statistically significant experiment, but it is an example of the kind of small-scale demonstration that can indicate to businesses that they might consider the use of more advanced methods. On this slide, you see some of the statistics that we gathered during the parallel development of the Trusted Gateway by two independent teams, one using conventional techniques and one using structured and formal methods. And you see significant differences in properties such as performance, code size, and the distribution of effort in the development process. So this was one early project that allowed us to demonstrate some of the potential benefit of advanced engineering techniques to one important company. On the next slide, I would like to add a personal note about another project. While in the CSR, I left academia and worked for a couple of years at a startup company called Transitive, developing dynamic binary translation software. The main product was a virtualization technique whereby instructions compiled for one processor architecture were dynamically translated into corresponding instructions for a target architecture. During the translation, optimizations might be performed to regain the performance lost because of the translation overhead. The translation software was therefore logically intricate. In setting up the design team, we applied VDM to analyzing some of the more sophisticated translations. The product became a key part of the translator that enabled Apple's migration to Intel architectures, even though it should be invisible to its users, which is why Steve Jobs called it the most amazing software you'll never see. Formal modeling in this context helped to provide a clearer conceptual basis for enabling complex translations, and particularly for bringing new engineers into the design process. Allow me to move on now to the third project I wish to describe, and I will discuss this in a little more detail. Deploy is a recent project led by my colleagues in the CSR. In the history of model-based and rigorous design methods, it is one of the most significant milestones, as it represented an attempt to transfer formal techniques successfully into several industry sectors. In the following slides, I will look in a little more detail at the structure of the project and its major outcomes. On this slide, I outline its major objectives of supporting reuse and adaptation of models produced in design, of developing methods that have been field tested and adapted for industry use, that are accompanied by deployment strategies, and that are open and are based on an open platform. The project was sponsored by the European Union from 2008 to 2012. The goal of the project was to advance the engineering of dependable systems by deploying formal engineering methods. We had learned from earlier projects, such as those I have mentioned, that advances were needed in the capability of design methods to describe the range of systems that arise in sectors that can potentially benefit from this development technology. However, we also realized the crucial importance of robust tools. Consequently, Deploy was structured so that advances in methods would be matched by increasingly capable tools, and these would together be applied to achieve industry deployment. In order to demonstrate the feasibility of this approach, the project brought together 3 groups of participants. First, academic partners who could develop the underlying methods and notations and could, of course, develop prototype tools. Second, service providers who specialized in delivering tools, training, and consultancy services to industry based on formal methods. And third, for the industrial deployment, 4 industrial partners from a range of business sectors with different levels of prior experience and different trading environments. In this project, success or failure depended on the industrial partner's ability to deploy the technology developed by the others. To an extent, the academics and service providers were both the teachers and the servants of the industrial deployment partners. They were, in a sense, our customers and our judges. The previous slide implied that we would develop methods and tools and simply deliver them into industry. To some extent, this is exactly what we had done in earlier projects like Conform. However, we learned there that new technology might be developed in research teams, but that such technology would naturally abstract away from the features of many application domains. We realized in Deploy that new dependability methods would only be adopted if they were tailored to the needs of application domains. Consequently, the Deploy project was cyclic in character. A first pilot deployment of the formal engineering methods and tools was followed by a full deployment study. The development and use of training materials was an essential part of the project. In particular, a 3-day block course was developed to provide a basic introduction to the core model-based development technology using the formal method Event B and its support tool Rodin. Between the 2 deployment studies, there would be an opportunity for the project as a whole to reconsider its technical objectives in the light of the pilot deployment study, in the knowledge of what is possible and what is more difficult. Let me make a few remarks about the technology that underpinned Deploy, the formal modeling language Event B, supported by the toolset Rodin. As with all the projects I describe, it promoted the use of model-based and formal techniques. Models are precise descriptions of computing systems. They may be descriptions of designs for systems that have not yet been implemented, or descriptions of existing systems. In order to ensure internal consistency, we have to verify properties of the formal models. These are called proof obligations. In order to gain confidence that each model accurately portrays the system we desire, we also generate validation conjectures. Proof obligations and validation conjectures are logical properties that may be proved with the assistance of a verification support tool, such as a theorem prover. A concern with many model-based design approaches is that the level of abstraction of the formal models is far above that of the implementation. In practice, this means that even if the abstract model has a formal semantics, formal verification of the correctness of the code implementation is complex. Event B seeks to bridge the gap by inviting the modeler to specify a number of intermediate design steps, each of which is individually verified. And when chained together, these form a verification of the final, most concrete implementation with respect to the properties recorded in the most abstract models. Each design step generates proof obligations, but the majority of these are quite simple and may be automatically checked by a proof tool. For the Event B formal method, the Rodin tool set provides verification support based on this principle. We now look at the outcomes from the pilot and main deployments in several of the industry sectors. Unfortunately, I don't have time to talk about all of them. First, we will examine the results of the deployment studies in the automotive sector, led by Bosch. This slide identifies the pilot and main deployment studies. The pilot deployment based on cruise control, logic, and safety feature verification, and the enhanced or final deployment based on engine start-stop systems for energy-efficient combustion engine management. As with our much older Conform project with British Aerospace, Bosch noted the importance of a disciplined approach taken to requirements analysis. They developed a technique based on the use of Michael Jackson's problem frames as a preparation for formalization in Event B. The graph on this slide shows the reduction by 40% in the overall number of requirements because of the elimination of requirements as redundant or otherwise unnecessary, and that reduction was achieved as a result of the modeling process. This slide shows the Bosch approach to the use of formal techniques as they tried it out in deploy. Several structured approaches, problem frames, and the RSML language for structuring requirements are used as precursors to formalization. Pre-formal analysis was seen as very helpful in obtaining a shorter and more traceable set of requirements. In the main deployment, Bosch noted a trade-off between the architecture of the Event B formal model, which was suitable for the automatic discharging of proof obligations, and the traceability of that model with respect to abstract requirements. An intermediate modeling representation in RSML was used to help bridge this gap. On this slide, I summarize the key outcomes from the deployment seen from the deployment partner's side on the left. So on the left are the views of Bosch, and on the right, the formal methods developers' views. That's the views from the people who produced the methods and tools. And as you can see, there were many positive features, narrowing the gap between informal requirements and formal models, but there were also some difficulties. For the second point on the right-hand side, for example, the scaling of formal modeling needs to be improved. And at the bottom of the left-hand side, the limitations of the formal methods in describing closed-loop control and real time. I comment at the bottom of the slide that the reality of deploying an advanced formal technique like Event B was harder than expected. but there was great value in having constant membership of the teams on both sides. The second example I should like to describe from Deploy was the application in the business information systems domain. This was with SAP. In SAP, teams of developers are familiar already with the use of model-based techniques, such as rigorous modeling of state transition systems and business processes using business process modeling languages. SAP's hope was that the use of formal techniques might assist analysis of the consistency of implementations with initial requirements. Global models of business processes are decomposed into local models linked by more models of communication channels. The figure illustrates how different techniques helped to ensure consistency. Note the importance of simulation in gaining confidence in models in the more abstract level. The requirements are necessarily at the top of the process. The requirements are necessarily informal. The outcome of the deployment studies with SAP are shown here. A very well-managed evaluation of the formal techniques and tools by SAP led to these main outcomes. The real value here is in the production of domain-specific tools that hide the formalism and automate analysis as much as possible. So at the end of our project, SAP were not using Event B directly, but they were using tools derived using Event B, but hiding the Event B within the tools. The remaining deployment studies are documented in the book of the Deploy project. There were many important lessons here about the development of a new dependability technology on the industrial scale. First, it is practical indeed for industrial engineers to deploy Event B. Second, the rigor of formal modeling improves understanding and reveals defects. And thirdly, Rodin and the plug-in tools significantly improved over the life of the project. These were unsurprising results. We have seen results like this in many formal methods projects. However, the last 2 points here, managing the requirements gap and getting the right tool for the job, these were relatively new lessons to us. Our deployment partners, the industrial partners, were very good at taking and developing the parts of the technology package that addressed the problems they felt were most important or urgent. They did not take the whole thing. During Deploy, we learned some hard lessons about what features are most important in such a project aiming to encourage the take-up of new technology. The first is that engineering is teamwork. Many methods for dependable design work in the small, but may not scale up to multiple users collaborating over possibly remote sites. Teams may be large and fluid, their memberships changing frequently, and support for task division and rework is needed, even in formal methods tools. The second lesson we learned was that tool quality is critical, even in a project developing completely new tools. Finally, a few points relating to the success of the project itself. The academic-industrial collaboration was strong throughout the project. There was a real dialogue. We, technology providers, did not always hear what we wanted to hear, and sometimes we presented the industrial partners with wonderfully elegant pieces of formal modeling that had little connection with real engineering. However, we were able to share and resolve our concerns, with the result that everyone came away from the project richer in knowledge and experience. The final CSR-based project I wish to mention addresses the need for model-based development in systems of systems. Here again, we used the deploy formula for a consortium. We had technology developers in this box, coupled with industrial deployment partners in this box, and a service and tools provider. The project was smaller than deploy and did not start with a pre-existing formal method, but instead aimed to develop model-based techniques and tools for this very challenging class of system. So here is a classical example of a system of systems problem. In responding to an accident, we have a number of essentially independent systems that must nevertheless offer an emerging service on which users, people involved in this accident, can rely. Here I show an extract from a high-level architectural model of the emergency response system modeled by our industry partners, INSEAL, in the Compass project. It shows the integration of independent systems managing the emergency services and the communications infrastructure. Yet together, these are expected to behave as one coherent system during the time of an emergency. Outside the SOS, system of systems boundary, are the systems that have the SOS experience. So the question we ask is whether we can manage evolution of this system of systems to a decentralized current structure while gaining assurance of the emergent global properties. A system of systems is an assembly of existing systems with these characteristics on which value and reliance is placed. When they work together in the SOS, the constituent systems deliver a new emerging service that they cannot offer individually. The challenges of system of systems, or SOS engineering, are enumerated here. Remember the conclusion from the Deploy project that engineering is teamwork. This is particularly apparent in systems of systems, where the constituent elements are largely independent and are free to evolve separately from one another, but must negotiate interfaces in order to ensure the global performance. Our approach in Compass is to produce clear models of the interfaces between constituent systems in terms of contracts. A contract contains a description of each system's expectations of the others in its environment and a statement of what it promises to do when those expectations are satisfied. The global SOS behaviors are verified by composing those of the constituent system interfaces. This slide shows the key technologies developed in Compass. Note that we aim to provide useful patterns, guidelines, and modeling styles in the well-established and supported SysML language, so that engineers can develop structured models without having to use the underlying formalisms directly. One of our partners, Atigo, provides mechanisms for developing SysML models. The semantics of a SysML model of a system of systems can be expressed using the formal Compass modeling language, CML. The global behavior is obtained by composing the constituent systems, and the formal framework enables tools, shown on the right, to analyze the constituent systems and their emergent behavior. And indeed, the tools framework has some features in common with that of RODA, the tools used in deploy. There are a large number of plugins offering services that correspond to the full range of simulation and analysis tools that our experience in deploy had already told us would be necessary. I will rapidly move to the Compass results. This slide indicates the assessment by Compass industry partners of the technology readiness levels of the different methods and tools developed in the project. This slide summarizes some of the more significant outputs and events to date. In red, I have shown some open questions, such as asking whether there are laws for the architectural refinement of systems, whether we can extend the foundations to probabilistic or stochastic models, continuous time models, or agent-based models. So what lessons can we learn from our experience of these projects? In this talk, I have reviewed our motivation for building the Center for Software Reliability around three principles: systems, not software; the importance of evidence as a basis for confidence, not certainty; and the need to address practice as well as theory. I have described several projects in which we gained experience by conducting a dialogue between industrial partners and academic technology creators. I would like to conclude by sharing some exciting new directions that we will be taking over the next few years. In cyber-physical systems, in areas like security and the verification of security, and in analyzing models of real events rather than models of designs. First, one of the most exciting areas of development for our research. The social fabric is a complex and increasingly digital system. I believe that some of the most interesting challenges facing researchers in systems dependability lie in growing confidence in urban systems that have smart elements. Ensuring the communities are sustainable includes demonstrating and enhancing their resilience to failures of component systems. We move from reactive urban systems to ones that use smart devices and data from many sources to inspire decision processes and enact change. At Newcastle, in a joint activity by the city and the university, we are creating Science Central, a former industrial area in the center of the city where we are creating a mixed community of researchers, students, businesses, and local residences. We are building laboratories, business premises, and houses with a smart and sustainable infrastructure, instrumentation, and the facilities to study these emerging cyber-physical systems. Within Science Central, we're creating a cluster of laboratories in relevant technologies, including a cyber-physical systems design laboratory, specializing in the engineering of dependable systems, using extensions of the methods I have discussed in this seminar, and some of which you will hear about from Professor Larson shortly. And we even have a new building due to open in 2017, and here is the latest design. To begin the work of the cyber-physical laboratory, we are fortunate to have had EC, European Commission, funding for a range of projects with academic and industrial partners beginning in January 2015. And here are some of our new and emerging partnerships. Well, my concluding remarks. I have indicated what I see as three important principles in our research, and in this talk I have reviewed several important projects that have produced positive outcomes in terms of better knowledge and adoption of advanced dependable systems technology. I believe that these demonstrate the value of a genuine dialogue between industrial practice and academic research. Our work has always been weakest when one side speaks but does not listen, when we push new formalisms to industries with little use for them, or when we demand perfect solutions from academia without putting effort into industrialization. The projects I have described indicate methods and tools that modestly meet industry needs. The clever technology may be largely hidden from view, and much of the value must lie in automation. However, formalism is a source of additional value, and we may not expect to get something for nothing. Investment in training does yield benefits. Finally, engineering is teamwork. Stable teams of focused practitioners and researchers really can succeed with advanced technologies. I would argue that only through such teams can we hope for the dependable systems our industries and communities require for the future. Thank you.